bungee jumping theoretically is a safe thing, yes? Right? Okay. Bungee jumping theoretically a safe thing, right? You can jump and you bounce and it's fun, right? What about chain jumping? Would chain jumping be safe? No. What do I mean by chain jumping? Right, like instead of having a bungee cord tied to your ankles, you have a chain tied to your ankles, you jump off a bridge, you get to the end of the chain, you stop very quickly, right? And so yeah, it would get grim, right? So here's a visualization of that, all right? So I hooked this up here. A visualization, yes. All right, so check it out. So I've got this thing here it's called a force probe. Basically, it's a bathroom scale. It measures force. So when I click collect, it measures. So right now there's no force on it, but if I pull on this thing, you can see how hard I'm pulling, or not enough, right? So real time, it measures how much force you're exerting. Good. Did you guys play with these at all last year or no? Okay, it's a thing. So there you go. All right. So, what I'm going to do is I'm going to roll this this cart down the track, and I've got it tied to a bungee cord, and we'll switch it in a minute and tie it to a chain. All right, and let's take a look. All right, so keep in mind the two axes here are force and time. Yes? Yeah. All right. So, and we'll talk about that in 1 second. All right, so let's do the bungee cord first. Oh, I guess worthy of pointing out. Well, I'll do it in a minute. All right, so here we go. So collect. And it gives us a nice little parabola, right? Okay. What's that? Well, I will, but we'll switch the bungee cord in a minute. All right. So what happened is, look, it took about 2 seconds for that to happen, right? Our velocity went, or the force, rather, I should say, went from 0 to maximum force. When did that occur? At the bottom when it stopped, right? Right? Because the more you stretch it, the more force there is, right? Okay. And then, as it bounced back up, the force decreased again until we got to 0, right? Make sense? All right. And it looks like if this is 10 newtons, it looks like that force is, I don't know, well, I guess we could, here, why don't we do this? So the force there at the top is 2.25 newtons. That's how much force we exerted. Okay? Half a kilogram. Okay, so let's swap the bungee cord out for a rope. What do you think the thing I wanted to point out was? Oh, well, right, I'm sorry. Yes, that's the goal, but they're about the same length, right? Right, to make sure that we have a controlled experiment, right? We're only changing one thing, right? So, out of my way, bungee cord. So, let's put the rope on. So, what's going to happen, you guys? How's the graph going to look different? It's going to give you a big spike, right? Because the change in momentum is going to be much more sudden, right? Again, this rope is about the same length as the bungee cord was. All right, so let's try it. Here we go. Collect. Oh, shoot, I wanted to save the other one. Darn it. Okay, so way more force, right? Okay, so let's do that. You guys talked about the integral a second ago, so let's take a quick second and find the integral. That's right, Adam. Take credit. Or Alex. Why did I say Adam? Sorry, Alex. Sorry. Okay, so I'm going to highlight this, just this one little blip here, and I'm going to click the integral thing. Kabam. So the area there is like 1.375 Newton seconds. I haven't shown you guys. Do you understand that a Newton second is the same as a kilogram meter a second? Yeah. Okay, I can show you that if you need me to. All right. So there's our thing. All right. So let me save the latest run, and then we'll do it again with the bungee cord. I'm mad that I forgot to save it.
That's okay, we can see it again.
I know, right?
I bet Marcus is
Just lost some credibility there. Whoa!
Yeah, I developed it.
So what have you done?
Wow. All right, here we go. So here's the bungee cord. You're going to miss it. Okay, so let's see if it worked. When I did it last hour, it didn't work as well as I hoped it would have, but it wasn't horrible. All right, so now let's highlight that same area. Find the area under the curve. So theoretically, it should be the same, right? I wonder how well it will work.
It goes down.
Well, right, it's more force over less time. I'm sorry, other way around. Less force over more time, so it should give you the same amount. Well, here, why don't we just do both? Oh, I see. No, so I didn't want run one. I just wanted the latest one. Okay. Well, yeah, came up quite a bit higher. All right, but theoretically they should have been the same, right? Okay. Questions though, you guys? All right. But anyway, the big idea here is the airbag gives you more time and less force, whereas no airbag gives you a lot of force, very little time. Cool? Questions? Thanks. But never as big as the chain. Say that again?
Isn't your velocity faster when you reach a higher velocity?
No, because so both of them reach the same maximum velocity before you're on a slack, because both of them are about the same length. So but then as soon as you get to this point, the bungee cord's going to start pulling up and slowing down, right?
It would.
Oh, I guess you're right, because it would have to, oh, there's the difference. You're totally right. Because, yeah, you got to stretch a little bit before your net force gets to 0. So you're right, you are going to hit a bigger, higher velocity. Very good, very good. All right, that hadn't occurred to me. All right, are we good, you guys? All right, cool. So, the homework. There's a big list up there. Let's see what we can get through here. All right. So before are we good with the two concept-y questions that were on here? Number 4, this one, all of the impulses are equal, right? What's the connection? They're all the same area, right? So if you find the area under each of these 3 curves, you get the same area. Good? All right. For number 5, you had to go through and say whether momentum was conserved in each of your dimensions. Under what circumstances would your momentum be conserved? Well, when we talk about momentum being conserved, we're talking about the amount of momentum you've got not changing. So what would cause the momentum of an object to change? Right, what causes the velocity to change? Net force. Net force, right? Momentum is conserved as long as there's no external net force. Okay? So, if you look at this first example, my x components cancel, right? I've got 4 and 2 newtons to the right and 6 newtons to the left. So my net force in the x direction is 0. So my net momentum in the x direction should not change. But in the y direction, it is going to change. So I've got more force up than I do down. Does that make sense? Are we good? All right. Here, let's see. So the x components of the 2 8-Newton forces are going to cancel out, right? And then we got 5 and 5. So here, again, your x components cancel out. What about your y components? Are the y components of my forces, am I going to have a net force of 0 in the y direction?
No.
No. So I've got 2 upward forces and no downward forces, right? Okay. This one, it turns out that your y components do cancel. Oh no, because this. Oh, I remember this one. Look where the 60 degrees is. Yeah, it's dirty cool. That's crappy. So anyway, if you go through the math, you end up finding out that the y components do cancel, Wait, that can't be right.
Yeah.
Oh, that is the same angle.
Okay.
Sorry. Yeah, sorry. Sorry. Okay, yeah, so the y components do cancel and the x's don't. Thanks. Are we good? All right, so keeping this in mind, you've just kicked a football through the air. The football's in midair. Here it is. There's the football. In the x direction, should the momentum be conserved? Yes, right? Because there's no horizontal forces. What about vertically? No, our vertical momentum is going to change because of the force of gravity. Good? Questions? All right, cool. So that's the concept-y stuff from that section. All right, so problems. Let's see. Somebody asked about 19. Okay, so 19. Oh, shoot. I put my graph in the wrong one. Darn it. I did that again. I had to restart my computer. And that was the effect. Okay, so here we go. So first thing, kilometers per hour. Kilometers per hour, what are you going to do? Convert to meters per second. All right, so let's see. Where do I have this in my folder? All right, so here we go. Our initial velocity is 41 kilometers per hour north. So I'm just going to put a little J on it. That's the same as 11.4 meters a second, J. And then our final velocity is 51 kilometers an hour in the, let's see, it's going east, right? So that's I. So that's the same as, if you calculate it, 14.2 meters a second in the I direction. So is everybody okay with those conversions? All right, so what does it ask us for? What's the change in kinetic energy? Well, find the kinetic energy associated with this. So it's half of the mass times this velocity squared, right? You got to use the 11.4, okay? And so that kinetic energy turns, oh wait, shortcut, darn it. So here was what let me just actually go through the calculation, even though I didn't do it on my paper. So what are we going to get? Half of 2100 is 1050 times this squared. So it gives you like 136,000 joules, basically. And this kinetic energy gives you about 212,000. And so the change in kinetic energy should just be the difference between those, right? So just subtract, and it gives you about 75,000 joules. Follow? Problems with it, you guys? I'm getting a lot of blank stares. Are we good? Okay, B, what's the magnitude and direction of the change in momentum? So change in momentum, you guys, by definition, change in momentum is mass times change in velocity, right? Okay, so let's find our change in velocity and then multiply that by the mass, right? So change in velocity is Vf minus Vi. That's the same as Vf plus negative Vi, right? So let's see, my Vf is 14.2 meters a second J. So Vf is 14.2 meters a second J, right? And then I want to subtract Vi. So instead of, my Vi, remember, was 11. Oh, wait a minute. Oh, my I turned into a J here. Darn it. Ah. Sorry, guys. Is that right? The Vf is east?
Yeah.
Vf is east. Okay. You guys go ahead. All right. So, sorry. Our Vf is east. Vf was 14.2 meters a second, right? And then my Vi was 11.2 north, right? So how do I subtract it? Isn't it the same as, instead of adding, I'm going to add it in the opposite direction, right? Okay. So here's my Vi. Oh, right. I guess you could just do that, right? Just do J minus I. Yeah, that works too. Yeah. All right. So anyway, so then find your hypotenuse. So your change in velocity ends up being Oh, I didn't write that down either. Darn it. Okay, so anyway, so you can find your change in velocity and then multiply it by your mass. You can see the change in momentum. Are we good, you guys, or no? Any problems? Okay. I feel like I'm 14.2 squared plus 11.2 squared. So this change in velocity ends up being 18 meters a second. You can certainly find this angle, right? So remember, you guys, the direction of your change in velocity is the same as the direction of your change in momentum, right? It's just scalar multiplication. Okay? So your change in momentum is just this times 2100, and so you end up getting like 3.8 times 10 to the 4th kilogram meters a second. Cool? Okie doke. So that was number 19. Number 20. All right, so 20 is this graph that I've got here. Because I did it quickly. I had to restart my computer right before class started. And all right, so what you're trying to do in number 20 is you're trying to find the angle that the ball is kicked at, right?
Yeah.
Or thrown at. Does it say what it just says? It's struck at ground level instead of level ground. Right. So, but the problem is you can't really tell the time at which it gets to the top of the path. It's 2-point-something seconds, but we don't know exactly what, right? So I guess maybe I should really quickly, maybe I'm being a little quick about it. Do you guys understand why that has to be the top of the path? If this is a problem about a ball being fired up into the air, at what point is the velocity magnitude the least? At the top, right? So smallest magnitude of velocity would correspond to smallest magnitude of momentum, right? Right, which is a separate issue. All right, so here's the idea. I know that my initial momentum is 6 kilogram meters a second, right? That means that my initial velocity is 6 kilogram meters a second over m, right? Good? And at the peak, the momentum at peak is 4 kilogram meters a second, right? Because it tells you that this is 4. You read the problem? All right? Which means that my velocity at the peak is 4 kilogram meters a second over m, right? Everybody point for me. What direction is the ball going at the top of the path? Horizontally, right? So look. What that means then is that I didn't erase my board. So let's think about this initial velocity. So my initial velocity is this way, VO. I know that it's 6 kilogram meters a second over m, right? What's true about the horizontal velocity of a projectile, you guys? It's constant. So this horizontal component has got to be 4 kilogram meters a second over m. And then there's a vertical component that we don't know. But we want to find this angle. Right? So that means, let's see, SOHCAHTOA, adjacent, and what cosine. So it looks like the cosine of theta should be 4 over m over 6 over m, right? Adjacent over hypotenuse. The m's cancel, you get cosine of theta is 4 over 6, and then just do inverse cosine and you're done. Does that make sense or no? Good? All right. I hope that, I don't know if the hint helps me, certainly. It said, hint, try to find a way to solve it where you don't need to know that time, and that was what.
If you did know the time, that makes a difference.
Yes, because then you could use the time to find this Vy component, right? Like if the time is 2 seconds, then this Vy must have been 19.6, right? 2 times 9.8.
Okay.
Good. All right. Where did I put my notebook? I just had it down somewhere dumb. All right, 31 is next on the list, jumping before the elevator hits. The classic question.
I took a question 26.
Oh, sure.
I think the answer you got is wrong.
Okay.
That's a bold statement.
Bill and I both got something different, and we think we get it right.
Hmm.
I got,
26?
yeah, 26. I got 2,646 newtons. I got some
2,000 who and what?
646 newtons.
2,646 newtons.
2,400. Go up on the board and show them solve it.
Force. Oh, here's why. Oh, I'm really glad you asked about this. My answer's right. I didn't mean that in a snarky way. No, it's a really common mistake. So check it out. So when you talk about impulse, and I hate that the book does this. So the book says, I don't remember how it's written, impulse equals F average times time, right? This is terrible notation. It's the net force that causes the change in momentum. All right? So that number that you got is the net force. Okay? So the idea is when your ass hits the ground, when you're falling off of this chair, the number you got is the net force. It's 2,600, I got 72, but that seems in keeping with what you had. You got 2648.
Well, mine, I calculated net force, I got 2,700, yeah, 317 for my impulse, and I divided it by your time. Just get.
Gotcha.
That is net force, yeah.
Yeah, so somewhere right in this neighborhood, give or take some significant digits. It's around there, right? Okay, but that's your net force. And so what hurts you is not the net force, but the force of the floor pushing up on your butt. So gravity's pulling you down with a force of 70 times 9.8. Which means that the force from the floor has got to be big enough so that this minus this is that. So you got to tack on the 686. Does that make sense? Good? Everybody? Thank you for asking that. That's something that I wanted to talk about because the book says F average and it's really frustrating because that's not. So, yeah. And I think I changed the wording of this from the way it was in the book. I think the book just says, what's the average net force or something? I don't know, but it says from the floor, so that's clear? All right, any problems with 26? Cool. All right, so where were we at then? 31, was that the next one I said I had to do? Was that the jumping? Yeah, jumping before the elevator hits the ground problem, right? Okay, so here we go. It says after the cable snaps and the safety system fails, an elevator cab free falls from a height of 36 meters. During the collision at the bottom of the elevator shaft, a 90-kilogram passenger is stopped in 5 milliseconds. Assume neither the passenger nor the cab rebound. So you're assuming your final velocity is going to be 0. Okay. So how do you guys go about starting? What do you mean when you say final velocity? There's 2 final velocities. Good. So the final velocity for the fall, right? So let's see. What do we know? We know that our vertical displacement is negative 36 meters. We know that our acceleration is going to be negative 9.8 meters a second squared. What's the velocity at the beginning of the fall? 0, and we're looking for the velocity at the end of the fall, right? So I think we can use this guy. 2a delta y equals v squared minus vo squared, right? Or you could do conservation of energy if you wanted, and that would work too. It amounts to the same thing. So you get 2 times negative 9.8 times negative 36 meters equals v squared minus 0. And so your v ends up being the number that I've written on this notebook over here, 26.6 meters a second. All right, so what is that number? Do you guys understand what that means? That's the velocity right before you hit it, right? Okay. So A says, what's the magnitude? I don't know why it says magnitudes. No, that's not a point. What's the magnitude of the impulse on the passenger? Well, so for question A, change in momentum is equal to your impulse, right? So it's just mass times Vf minus Vi. Well, his mass was 90 kilograms. His final velocity after he hits the ground is 0, minus, be careful, there's a small mistake on the board. What's the initial velocity? It's this, kinda. How did I solve this? What did I have to do? I took a square root. Negative. Why? You're going down, right? Oops, that's a minus. Cool. So your change in momentum is going to be 90 times 26.6, and you end up getting 2,391. And you can either write that as Newton seconds, or you can write it as 2,391 kilogram meters a second. For whatever reason, usually impulse, when they ask for impulse, they want Newton seconds. And if they want change in momentum, they want kilogram meters a second. I think the distinction is silly because they're dimensionally the exact same thing. All right, everybody good up to there? Problems? Okay. So then B says, what's the average force from the floor on the passenger during the collision? So this is exactly the same thing we just did a second ago with your butt hitting the floor, right? So let's see. Change in momentum is net force times time. So my change in momentum is 2,391 kilogram meters a second. That's going to equal my net force times my time of 0.005 seconds. And solve it, and you find out that your net force is 4.8 times 10 to the 5th newtons. And that's the answer I gave. Why didn't I add on the weight? I did just a minute ago. It's the exact same thing. It's the same as the chair problem, except you're falling farther. What would your weight be? Oh. Yeah, it's way smaller, right? 90 times 10 is 900. So we're talking about 48,000 newtons plus 900, right? So it's an insignificant amount. Okay? So it doesn't actually change your answer. Cool? Problems with that? Okay, so everybody good with A and B? All right, C says, what happens if right as you're about to hit the ground, you jump up so that the instant you hit the floor, you're leaving the floor of the elevator with a velocity of 7 meters a second relative to the cab floor? So, Jackie just said subtract. What do you mean?
Well, the final velocity, 26.6, you subtract 7 from it.
Exactly. So the idea is instead of you moving at 26 meters a second when you hit the ground, now you're moving at 19 meters a second when you hit the ground. And then you solve it the exact same way. Yes?
Is that to say if you would be able to throw off 26
Theoretically, I think so, but then the ceiling of the elevator becomes an issue.
you blow it off?
So I think that I believe that yes, if the well.
When you hurt yourself, like accelerating that fast out there.
Yes, because what you my yes is yes to you, not my yes to other Alex. Sorry, I didn't know who asked it. So let me finish. So yes, you would be basically hitting the ground at a velocity of 0. But you're right that would take a tremendous amount of force, and that force of you changing your velocity that quickly would be the same as you hitting the ground. It's like Superman saving Lois Lane when she's falling, right? Like it's not that much better than hitting the ground, right? She's still changing her velocity very quickly, right?
It's actually worse.
It's a bigger change in momentum, right? Because instead of going from down to 0, it's down to up. So, all right. So yeah, I think Alex, to answer your question, I think you're half feet away. Flatten the absolute point. All right. Are we good up through 31?
Yeah. This is a different question. On 37, the amount of time that person's in contact.
Well, give me a second to read the problem. I don't remember off the top of my head.
It says the further players in contact with the ball for 3 times 10 to 23rd seconds, which is like 9.5.
Oh, that has gotta be a typo.
Oh yeah. It was supposed to be like negative.
I think it's supposed to be negative third.
Well, it's 9.5 billion.
So that's a problem. Yeah, that's a typo.
Is that a point?
Yeah. All right, hey guys. So 37. Jack is exactly right. That time there, the 3 times 10 to the 23rd seconds, that's a typo. Let me see if I can figure out what the real number was supposed to be. It was supposed to be -2 or -3. Oh, really? Oh. No, then it doesn't affect the answer. Because the next sentence says the foot of the player is in contact with the ball. The force is given by, and then it says for 0 between, and then it gives the right time. So it doesn't matter how long the foot is in contact. You're answering the question just for the first 3 milliseconds.
Wow. I did it the other way, and my answers are hilarious.
I gotcha. All right, I'll give you the point though, because I can still see that might have been confusing. All right, so anyway, if you didn't do that problem because you were thrown off by the number, go back and do it, because that is definitely a problem that you need to know how to solve. All right? And again, to be clear, it should say 10 to the -3rd, not 23rd. Good? All right, and Jack, I will give you the point. Yes. Yeah, I still had a list here. So, all right, so how are we doing on time? We're okay. All right, 32. Okay, so we've got a graph here, right? It's force. We've got a graph here that's force versus time. All right, here are the things we know. We know that the car has a mass of 5 kilograms. It tells us that the graph at the right gives us the x component of the force, which is important because we're just interested in the motion along the x component for the x-axis. It begins at rest at time 0, so our v0 is 0. The scale on this is given by Fxs equals 5 Newton meters, or sorry, 5 newtons. So this is 5 Newton meters, so 5, 6, 7, 8, 9, so it looks like it's 10 newtons up at the top, and -5 newtons down here. All right, so what's my initial momentum going to be, you guys? 0, right? So that means that for the purposes of this problem, at any given instant, the momentum should equal the change in momentum, right? Because we began at 0. Follow? All right, so how do I take the information about this force time graph and translate it to momentum? Area, right? It's the integral. So to do the first question, you're just going to find the area under the graph for the first 4 seconds. So that's going to be 2 times 10 is 20, plus half of 2 times 10. So 20 plus 10 is 30. And there's your momentum there. Did I do that too quick? For B, same idea, except you've got to subtract out the negative area, right? Remember, negative area means you're losing momentum, right? Good? All right. C says, what's the velocity at t equals 9 seconds? Well, we've got to find the momentum after 9 seconds. So we need to find the total area of this thing. So let's kind of break it up into chunks. So this area here is half of 2 times 10, right? So 10. This area here is 2 times 10, so 20. This is the same thing, so that's still 10. This thing here is 1 times -5, so that's -5. And both of these two chunks combined make up another -5, right?
So the momentum at 9 seconds would be 30.
I agree with that.
And then dividing it by the mass would give you 6, not 5.
I think I might agree with you.
Yeah.
Yep, you're totally right. So that's a genuine bona fide point. All right, so yeah, so your momentum here, you're right, would be 30 kilogram meters a second. So yeah, so your velocity, you're right, would be that divided by your mass. You're right, it gives you 6. Point! That's
Wait, I
2.
was confused as to the eyes for the whole problem.
What are all the eyes there for?
The negative square
Oh,
root.
to this,
It's on the x-axis, yeah. And unfortunately, drawing the little hats is too much of a pain, so.
Those are all false.
Yeah, hang on, let me make a note real quick. What is this, chapter 9? So I owe you, Jack, which one did you ask about?
It was 37.
Number 37, and then this one's number 32. Okay, got it. Yeah. Is that a mistake also?
No, I got 38.
Oh, it's 37 and a half, but with sig digs.
Oh, wait. It's 40.
Sig digs, sig figs, whatever you want to call it. I guess sig figs is the... You good? Okay. All right, everybody happy?
Yeah.
Cool. So that was 32. So I think the only two we haven't done yet are 26 and 35, right? Oh wait, we did 26.
Yeah.
So we've just got 35. Look at us kicking A. All right, 35. So almost the same idea, right? You're still trying to find the area under the curve. So let's see. It says the graph shows an approximate plot of the force magnitude versus time during the collision of a 58-gram superball. So our mass is 0.058 kilograms with a wall. The initial velocity is 34 meters a second. The ball rebounds directly back with approximately the same velocity. Right? Initial, final. One of them has to be negative, right? So my change in momentum is going to be mass times, what, V minus VO. Sorry, I keep... So if you figure that out, you end up getting... What number is this? 35? 3.94, do I believe that? I think I do. So you get 3.944 kilogram meters per second. So that's the change in momentum. Good? Right, now, the question is, what does this value have to be to make what property of this graph equal that number? Don't we want the area under this, right? The area under this would give me the impulse. And the impulse is equal to the change in momentum, right? Does that make sense? I know how much my momentum changes. I understand, let's see it. So it looks like it's telling me that the force increases linearly for 2 seconds, stays constant for 2 seconds, and then it decreases linearly for the last 2 seconds. So let's write an expression for the area of this thing in terms of F max. And there are a few ways of doing it. So one option is to use the trapezoid rule. So if you use trapezoid, remember the area of a trapezoid is 1/2 of base 1 plus base 2 times height. Good? Or you can do what I did because I don't like trapezoids. I have an issue with them. Is take this chunk, take it off, flip it over, and put it over here. And then you can see that the area is just 4 times F. Good? All right, 4 watts times F. Milliseconds. 0.004 times F max. So we've got this equals 0.004 times F max. Divide both sides by 0.004 and it gives you that. Make sense? Questions? Okay. I think we hit everything that was on the board. Is there stuff that wasn't on the board that you guys want to go over? 31.
We already did those.
So 31. So 31. We did A and B, right?
Yeah.
31 C and D are the same as A and B, except instead of using -26, you use -26 minus 7. But then the process is the exact same. Does that make sense?
Yeah.
Good.
But could be negative 0.0.
No, because you're jumping. So you're moving down, but your jump is up. So it's technically negative 26 plus 7.
Yeah.
Gives you negative 19. Okay, then yes. Yes. All right. Are we good? What else do we need to look at? Did we get everything?
Yeah.
We didn't go over 37, which is making me nervous, and we didn't talk about 36. Did you guys get 36? We got 5 minutes. Should I go? I think it's the only one on the problem where you have to take an integral. Oh no, 37 has an integral also. Should I do it? What's that? Okay, so let's do 36. 37 is similar, and if you guys want later this week, I can go over it. Okay? All right, so for 36, here's what we know. We know that the mass of the hockey puck is 0.25 kilograms. We know it's initially stationary, so our initial velocity is 0. Negligible friction at time 0, a horizontal force begins to move the puck. So the force at time t is given by 12 minus 3t squared in the I direction, and that's newtons. All right, and it acts until the magnitude is 0. So the force is going to start at 12, right? And then as time goes on, the force is going to get less until you get to 0. Okay. So A says, what's the magnitude of the impulse on the puck from the force between t equals 0.5 and t equals 1.2? So look, you guys, if the force is fixed, don't write this down, but just listen. If the force is fixed, then you can just do net force times time to find your impulse. But here our force is not fixed. It's going to vary with time. So to solve it, what do we have to do? Integrate. So my j is going to be the integral of my force with respect to time, and I'm going to integrate between my two times, specifically 0.5 and 1.25 seconds. So 0.5 and 1.25 seconds. So it's the integral from 0.5 to 1.25 of 12 minus 3t squared dt. And integrate. So the integral of 12 is going to give me 12t. The integral of 3t squared is t cubed, right? Let me pause there for a minute. Integrals. Are we all okay with how I got this? It's what do you take the derivative of to get that? And here's our answer, right? And then you evaluate it at 1.25, you evaluate it at 0.5, and then you subtract. So you're going to get 12 times 1.25 minus 1.25 cubed minus 12 times 0.5 minus 0.5 cubed. We'll solve that, and it gives you whatever I said the answer was on the sheet. 7.17 Newton seconds or 7.17 kilogram meters a second. Either way is fine. All right. And then B is the exact same, except it says, what's the change in momentum of the puck between t equals 0? So my lower time is going to be 0 instead of 0.5. And the instant at which the force is 0. So set this equal to 0. What does t have to be to make your force 0? 2, right? Because 12 minus 3 times what squared would give you 0? Well, let's see. 3 times 4 would be 12, so, 2 squared, right? So you just integrate between 0 and 2, and you do the exact same thing. Make sense? All right, and like I say, 37 is similar. Once you figure out that issue with the time, then, we can go over to T1. Good. All right, so tomorrow you got the next chunk. I'll go over questions on the next chunk tomorrow. I also, tomorrow will have, I started putting the test together, and I've got, like, sort of 2 lists of questions. One of them is going on the test, the other one I'll give you those tomorrow. All right, so I'll give you some practical choice questions tomorrow, so thank you. All right?
Thank you.